So, a function is, a graph is concave upward when what is true?
Is positive.
Yeah. Want to know when y double prime is greater than 0. So to find y double prime from y, what do we first need to find?
Y prime.
Can someone tell me what y prime, it's with function with respect to x, is equal to? Can someone tell me what y prime is? You can just tell me what it is. What is it, Moses?
Over 1 plus x plus x squared.
1 plus x plus x squared. Yes, by the fundamental theorem of calculus part 1. If you have a function and you take the integral and then you take the derivative, where are you?
Back.
You're pretty much back exactly where you started. So if that's y prime, what's y double prime with respect to x going to be? Well, what's another way to write this? Exactly. 1 plus x squared to the negative 1. So this is going to be negative 1 plus x squared to the what?
Negative 2.
To the negative 2 times what? 1 plus 2x. Let's just rewrite that a little bit. It's going to be negative 1 plus 2x all over what?
You need to add c, don't you?
No, we're taking the derivative. There's no c.
Right.
Wait, is the bottom going to be negative?
Doesn't matter if the top or the bottom. It does the same thing. Like this. Is that okay?
Yeah.
So if we can write this. Oh, and it's squared. Thank you. That's very important. Yes. Okay. Got it. Okay. So you're trying to find out when this is greater than 0. We want to know when this is positive. So if we're looking for things to figure out when they're positive, what do we generally look for first? When they equal 0. You know that this right here, this fraction equals 0 only when what is true? The numerator is equal. So when does negative 1 plus 2x equal 0? That's it equals 0 when
Negative
1 plus
1/2.
2x is equal to 0, which is when 2x is equal to negative 1, so x is equal to
Negative 1/2.
negative 1/2. So we know it equals 0 when x is equal to
Negative 1/2.
negative 1/2. So this is x, and this is y double prime of x. We know the second derivative is 0 when x is negative 1/2.
Yeah.
Are there any other places where it's equal to 0?
No.
No. So at this point, what do we need to do?
Plug in negative
Test
infinity
values.
and-
Well, yeah, true, but there's an easier, we don't really need to go that quite of extreme. Can someone tell me, what's one thing you can tell me about the denominator of this fraction?
It will always be positive.
It'll always be positive. It'll always be positive. So no matter what you plug in, just realize it's always positive, right? So what's a number to the right of negative 1/2 that's really easy to plug in?
0.
Plug in 0. When you plug in 0, what do you get? Negative 1. So over here it's going to be negative. And then what's a nice number to plug in over here?
1.
How about, yeah, or negative a billion, right? 1 plus 2 times negative a billion, but there's this negative sign on the outside, right? So that makes it,
Positive.
so it's positive over here. So we know it's concave up when, what?
From negative
X is
infinity.
less than
Yeah.
negative 1/2, which you could also say, or stated way. Which way? You could say, or stated as negative infinity. Is it a closed bracket right there? No, it's not a closed bracket. Since y double prime of x is greater than 0 when x is less than negative 1/2. Does that make sense, everybody?
Yeah.
So the key thing here is the fundamental theorem of calculus part 1 allows you to say this right here. FTC part 1. FTC part 2 is what allows you to do what? Evaluate integrals. These are separate things, but pushed together, they're called the fundamental theorem of calculus. Yes. Yes. Think about this. We're trying to find, we want h prime of x, okay? We want h prime. What's one thing about this problem that is a little different? What's one thing? Okay, good. You saw that. Sometimes people just don't see that. First thing is this. That's different. Usually you see just what?
X.
X. You just see x. And what's the second thing that makes you guys go, heart palpitations? What?
Arctan.
Yeah, you guys don't like this for some reason. I'm not sure why. Okay, so to make it seem a little bit better, how about we write it like this? 2 to 1 over x of tan inverse of t dt, right? Now here's the thing. If you were using the fundamental theorem of calculus, and let's just say it was this, 2 to x. Can you tell me what, let's say g of x. I'm going to redefine this. Let's say g of x was this. Slightly different. Can someone tell me what g prime of x is? Using the fundamental theorem of calculus part 1. We just used it. What is it? It's going to be
tan inverse x.
tan inverse of x. Done. There's something invisible that's floating outside of the tan inverse x. What is it?
A positive 1.
Why a positive 1? D dx of
T.
x.
T. X.
X of x. What's the derivative with respect to x of just x?
1.
1. This equals tan inverse of x. Exactly. So let's go back to h prime x. So what's the first part you're definitely going to have? What is h prime of x going to definitely have in it? What's it definitely going to have in it? Tan inverse of 1 over x, correct, times what? D dx of... So what rule did we just use? We just used the chain rule. The chain rule still applies here. We're still taking the derivative. But instead of throwing in x, what are we throwing in? 1 over x. What's the derivative? Oh, come on, it's not that bad. So yeah, they would expect you to do one more. What's the derivative of 1 over x? Yeah. Negative x to the 2 tan inverse of 1 over x. All done. That's it. You're done. That's it.
Okay.
The only thing they're introducing is instead of plugging in x, you're plugging in 1 over x. It's not 1 as its derivative. That's it. For example, when we did the power rule, when you guys first did the power rule, everybody, when you guys first did this, d dx of x squared, what does that equal? 2x times what?
1.
Times 1. Why just 1?
Because the derivative of x.
D dx of
X.
x. Exactly. Right. What happens if, but then you learn later, like d dx of, I don't know, 2x squared plus 4 squared. What does that equal? 2 times 2x squared plus 4 times the derivative of what? 2x squared plus 4, right? So you're like, oh, chain rule, yay, chain rule. Have you?
So the chain rule is really always doing the chain rule?
Yes, the chain rule never stops. You never. No. The chain rule's always there, but when we think of the chain rule not happening, it's just when it's pumping out a 1. That's it. Your chain rule's always there. It's not like math stops existing, right? I mean, the thing.
think so.
No, come on, we're good. The integral. So to figure out what the integral is, you need the limits of integration and the function. You need the limits of integration and the function. Let's do the first one here.
And it's defined from 0 to 1.
Oh, it's actually telling you it's 0 to 1. Oh, I'm sorry, I totally did.
It makes it so much easier.
Well, it makes it easier, but you don't absolutely need that.
No.
Okay, so for this one, you know it's the integral from 0 to 1, correct?
Yes.
Now for this, when you're figuring out the summation here, usually you see this. You have the limit as n goes to infinity, right, of the width, right, times the sum of the heights, correct?
Yes.
In this case, the width and the heights have been multiplied together. What's another way to write this? If I wanted to separate this out, what could I factor out?
1 over n.
1 over n, right? I could write this as the summation of I equals 1 to n of 1 over n times what? I cubed over n cubed, right? That's equal to the summation of I equals 1 to n of 1 over n times I over n quantity what?
Cubed.
Quantity cubed. So this is going to be, we know it's going from 0 to 1. So 1 over n will be the width, correct?
Yes.
So in this case, what is the function? This is just x cubed dx. That's just the integral from 0 to 1 of x cubed dx. This is exactly what you would get if you started using a Riemann sum to evaluate the integral from 0 to 1 of x cubed. So the next one is just a little bit more tricky. You have to be a little careful. You know it's the integral from what to what? 0 to 1. And does it actually put the width out front?
Yes.
Yeah. So here's the, what does that represent? The first what? The first height. That's the first height. And this is the
Second height.
second height, right? If this is the width right there, if 1 over n is the width, what's the first, and you're starting at 0, what's the first x value you're evaluating? 1 over n.
Yeah.
And then you're plugging in 2 over n. And then you're plugging in
3 over n.
3 over n. So you could rewrite this right here, just so you can see this. You could rewrite this as the limit as n goes to infinity of 1 over n times the summation of I equals 1 to n of, what's the function? The square root of I over n, right? What's the function?
Root x.
root x dx.
Don't you also
That's
have
it.
to find,
It's just to evaluate.
And then it says evaluate. So can you? Okay, yes. Now once you've written it as an integral, these are actually pretty decent. What's the integral of x cubed?
1/3.
1/4 to the 4th from 0 to 1. So what's that equal to? 1/4. Correct. This one right here. This is the integral from 0 to 1 of x to the 1/2 dx. Can someone integrate that for me? What's the power of x going to be? 3 over 2. So what has to go out front? 2/3, and you're doing it from 0 to 1. So what's this equal?
2/3.
2/3. All done. All done. This right here is definitely something that you could see on an AP test as a multiple choice question. Because this tests your knowledge of calculus. This has very little to do with algebra. This is just you recognize, oh, Riemann sum, so therefore, oh, simple, oh, look at that. This is just calculus. This is like 99% calculus, and then your ability to go 1/2 plus 1 is 3/2. The reciprocal of 3/2 is 2/3. That's the only algebra you really need for this. Yes? 1 over x squared plus 1 dx. Oops. Don't bump the table. Careful, careful. Dx. Yep, great. So this first one, what's the integral of x cubed? Yeah. 1/4 x to the 4th from 0 to 2 minus 6 times 1/2 x squared from 0 to 2 plus 3 times what? Yeah, once you see that, is this pretty straightforward? 0 to what? 2. So what does this turn into? 2 times 16 over 4 minus 6 times 4 over 2, right? Plus 3 times tan inverse of 2. So what do you end up with here? 8 minus 12 plus 3 tan inverse of
2.
Tan inverse of 2. So you end up with negative 4 plus 3 tan inverse of 2. Is that a number?
Yeah.
Yeah. Relatively clean. Yeah, it's kind of nice. Now, what's the best thing you can do to start off with the second one? If this is the first one, what's the best thing you can do to start off with the second one? Simplify. That's 1 to 9 of 2 plus the square root of t minus 1 over
T squared.
dt. I don't have. Do you see why that's true, everybody? Does everybody see why that's true? What can you? We're canceling, right? Are we good? Does that make it a little easier to do? What do you think? Yes, it does. So you have 1 to 9 of 2 dt plus 1 to 9 of the square root of t dt minus the square root of 1 integral from 1 to 9 of t to the. What's the first one come out to be? What's the integral from 1 to 9 of 2? Nope. Just give me the final answer.
It's 242 over.
It's from 1 to 9, and the box has a height of 2. 16. Thank you. 16 plus. And what's the integral for here? What's the integral of the square root of t? T to what power? 3 over 2. So what goes out front? 2/3, and you're going from 1 to 9. And this one is, what's the power going to become? Negative 1. You go up, up, ever careful, up. What goes out front? Negative, right? And you're going from what to what? 1 to 9. We good with that? Does that make sense? Yeah? You just got to be careful with your L. This went to 16 plus 2/3 of 9 to the 3/2.
8. 1 to 9.
I understand. It's 1 to 9. I haven't closed. I'm sorry. What's the problem here?
Yeah.
I haven't finished writing it. Is that okay? Yeah. Minus negative 1/9 minus what? Negative 1. Are there a lot of minus signs in there you have to be really careful about?
Yeah.
This negative sign right here, where's this negative sign going? That negative sign is going right here and right there. But when you actually use the, what did we use right here? We used the fundamental theorem of calculus part 2, right? FDC part 2. you subtract the 2, correct? There's a lot of negatives, so is it really easy to get the algebra wrong here? 16 plus what? What's 9 to the 3 halves? 27? It's the square root of 27, so it's 27 times 2/3, which is what? 18 minus 2/3 minus what? How many ninths? 8 ninths. Good. Yeah, good job. Anybody have a final answer for this? Anybody? 32 and 4 ninths. I don't like writing it like that. So what is that actually? What's a better way to write that? Oh, come on, you can do that in your head. 98, 302, right?
288. It's 392 over 9.
392? 292?
392.
Thank you. I was off. Over what? 9. Do we agree with that answer? Okay, do you want to see how to do this on your calculator? So we have this. It's nice. So let's go back out into the main screen. So this is the updated operating system, so some of your calculators will look like this, some will not. But in math, it's right here. You've probably seen it. Fint right here. If I press enter, it's going to look like this. And you actually just get to plug in 1, 9. What function am I going to put in here? Y1. And I'm integrating with respect to x. And I hit enter on this thing. It's going to think for a while. And hopefully, is that the same thing?
32 and 4 ninths.
It is. It absolutely is. Okay. So this is on an 83. Now we go to math. And you go down to right here, Fint. So now you have to do the proper form. And I always forget what order it is, but I'm pretty sure it goes vars, y vars, function y1, start value, I think, and I'm flying on the edge of my pants here, 1 to 9, and then we're gonna differentiate with respect to. I think that's it. It is not. So let's actually look up what it is. Y1. Oh wait.
It should be prefaced with no idea.
I don't, because I updated the operating system. I can't remember. Y1 and then X like this. Let's try it that way. Ooh! Oh, okay, fine. This is nice, exciting. So we go math, and then it's 9, I think. Yep, 9. So it is the function first. So vars, y vars function, and then it's the X, and then it's 1, 9 like this.
So it's the order we didn't try.
Well, there's 24 orders.
Well, I doubt it's going to go 9, Y1, X.
Well, why not? Who knows? Okay, is that the same answer?
Yeah.
Yeah, it's the exact same answer. So I'll cut this in here. So is this something you've seen?
Question that
Yeah. Well, no. Well, that's actually not referred, but you're totally right. If you evaluate an integral, so let's take a look at this. If I gave you a function like that and there was some perfect symmetry right there, if this was 8 and this was 8 right here, if you did the integral from 0 to, let's say, b right here, what would the integral come out to be? 0. You're actually finding net change all the time. So if you do this in a practical application, I could ask, find the displacement of the particle. The displacement is the net change. That's what displacement means. Displacement means net change. So if we're going to do this, we can use integrals to do this. Find the displacement from 1 to 4. How do you do that? You're just doing the integral from 1 to 4 of t squared minus t minus 6 dt. If this comes out to be negative, what does that tell you about the displacement? It went backwards. It ends up back before where it started at time equals 1. If the displacement was positive, over this time interval, overall it moves forward. Exactly. Got it. What about distance traveled, though? If I go 10 miles forward, 20 miles back, and 10 miles forward, how far have I traveled? 40 miles. Finding displacement is pretty easy because what are you doing? Just what?
The integral.
Just the integral. But if I go 10 forward, 20 back, and 10 forward, the displacement would be 0, but our time to the distance.
Separate integrals for the.
You have to find separate integrals. Okay, so for this, but what are we specifically looking for? So if a particle is on a line and it's going like this, and it stops, and I want to know the distance traveled, what points are we very interested in?
The endpoints.
Nope. Well, where it stops. That would be the displacement, yes. But if I do this whole thing, where it changes direction. You're very interested in knowing where it changes direction. Because when I said 10 miles forward and 20 miles back, that's defined as where it changed direction.
'Cause it has to
A
stop.
particle changes direction when what is true?
When the velocity is 0.
Changes
Does it
from-
have to?
No.
Does it have to change direction?
Changes sign.
No. But
When-
if the particle changes direction, the velocity must be
Change.
0 right there. If it does, the
If it's
velocity
on
must be
two
0.
dimensions.
Yes. Sorry.
I mean 1 dimension.
So we are looking at particle on a line, which is 1 dimension. Yes. Okay. We're looking at particle on a line. Okay. So here's the deal. You are very interested in finding out where the particle changes direction, which is the same thing as finding when the particle changes direction, right? So if we look at this function right here, v of t is equal to, what is it, t squared minus t minus 6. Is that it right there?
Yeah.
Is that correct? And we're looking for the interval, the time interval from 1 to 4. It says, what is the distance traveled during this time period? What would be one thing to find first? What would you go for first?
Find zeros of the function.
Find zeros of this function? Okay, so let's find zeros of this function. So when does this equal 0? Well, can we factor this? T minus 3 times what?
T minus 2.
T plus 2 equals what?
2.
0. So t is equal to what?
Negative
3
2
or
and 3.
a negative 2. We're only looking at this interval, so what's the only one we're interested in?
3.
We're interested in 3. Okay, so what do we know? At 3, the velocity is 0, but does that necessarily mean it changes direction?
No.
No.
We have to do the
First derivative test, right? So time is equal to 3, and we're looking at velocity. We know the velocity there is 0. And what's the function? T squared minus t minus 6. And we're going from 1, and we're going to 4. So what's the number between 1 and 3? 2. Put 2 in here. 2 squared is 4. 4 minus 2 is 2. 2 minus 6 is...
Negative.
So we know here it's going to be negative. Between 3 and... You have to use a fraction here, so what are you going to use? Well, you have to evaluate something. So v at...
4.
We can't use 4.
Oh. It's a closed interval.
Okay, 4. That's fine. V of 4 is going to be 16 minus 4 minus 6 is 6. So it's going to be positive, right? So from 1 to 3, you know this thing, the velocity is negative. And from 3 to 4, it's going to be positive. So what should we specifically evaluate to find the distance traveled? For distance traveled, does it matter if it goes forward or backwards?
No.
No, it's still, distance traveled is always what? Positive or 0, right?
Do one integral from 1 to 3 and 1 from 3.
Yeah.
So we're doing from 1 to 3 of the velocity. I agree to that. That's correct. But we know if we do that, what's it going to come out to be? So what do we do to this? And we add it to the integral of 3 to 4 of what? V of t dt. Do we need to make that the absolute value?
Shouldn't you, just as a formality?
You absolutely can. So what you can do is you can break it apart and as a formality do that. So what are you doing here? You're just making sure that anything that goes below the x-axis actually goes
Above.
above. Do you have a mathematical a function for that? It's called the absolute value. So if you do this out, this is a definite integral, this is a definite integral. You make sure they're both positive, and then what do? Add them together. But you need to know specifically where to segment it. What did our math, our algebra was specifically to find this value, right? Do you agree with that?
Yes.
So if we do this, how can we find the distance traveled?
Yes.
Absolutely. Now, the last thing I want to show you here is, can you use the absolute value function on your calculator?
Yes.
Absolutely. If I do this function, and I'm going from what, 1 to what? 4.
3.
1 to 4
Okay.
of, what is it, y1, right? y1, and it's d what?
X.
dx, and I press enter. What is this? That's the what? This is the displacement. Absolutely. That's the displacement. What do I need to do in order to find the distance traveled?
Yeah.
I could do 2 different integrals, but if I don't want to do 2 different
You
integrals,
absolute value the, no, you don't.
what do you do? Boom. What do I get?
Wow.
It's going to think for a little. Why does it take a little bit longer?
Because it is the same
That's, well, what's the thing? Yes, because it's doing the absolute value. That's the only thing it's doing differently. So here, what did we get here? Hey, we just got, from our calculator, we just got the, oh, let's use a different color here. What is this? That's the displacement. And what's this right here?
Distance traveled.
Distance traveled, yeah. Can you do the exact same thing on your 83? Yes.
Yeah.
Is the ABS function there? You just do ABS and in parentheses. What do you put in the parentheses? Y1. Absolutely. We're not quite done yet, so please don't pack up.